talk about exponential and logarithmic functions. Okay. One thing that I wanted to ask you, why do you think these two functions are in the same chapter? Why do you think that they are together? If you remember, if not, I will tell you. Does anyone remember? Why are these two functions in the same chapter together? Anyone? Any suggestions? Any ideas? So you have something there. So the answer is they are inverses of each other. They are inverses of each other. So the exponential function and the logarithmic function are inverses of each other. That is the reason. Okay, so let's refresh our memory on how they look like and graphs and properties, and then I'll come back to the idea that they are inverses of each other. Can anyone give us an example of an exponential function? Can anyone give us an example of an exponential function? How does it look like? Why do we call it exponential? No one remembers how anything about exponential functions, how they look like, and
be 2 to the power of x. Would that be
excellent? 1? Yes, absolutely. So an example is 2 to power x. So it's called exponential because the variable is the exponent, not the base. So this is the base, and this is the exponent. That's why it's called an exponential function. So there are two possibilities. So in general, so this is f of x equals a base a to power x. An example is when a is 2. So there are two possibilities. One possibility is when a is a number greater than 1. And Landon just gave us an example. This is a perfect example. F of x equals 2 to the x. And there is another possibility. When a is very small, between 0 and 1. Can anyone give us an example between 0 and 1? A number between 0 and 1? Any number?
0.5.
Correct. 0.5, which is 1/2 raised to x. Perfect. So a number between 0 and 1 will be indeed 0.5 or 1/2. We prefer 1/2 raised to x. It doesn't matter. You can write 0.5. So a number greater than 1. Notice one thing, that this particular value, the base, cannot be a negative number, cannot be 0, and cannot be 1. So a cannot be 0, a cannot be 1, and a cannot be negative. And you can ask, wait a minute, what are you talking about? I can raise 0 to the 3rd power. I get 0. I can raise 1 to the 15th power. I get 1. I can raise a negative number to any power I want, and I get a number. Why are these banned when it comes to an exponential function? For the following reason. More than one, but this is one of the important reasons. Its inverse function will not exist. The logarithmic function cannot have a base of 0, cannot have a base of 1, and it cannot have a negative base. That's why these are all excluded. They're not options for the exponential function. Although we can determine these numbers easily, but they're not allowed because of the log function. Okay. Now, of course, there are two different shapes and there are two different graphs. So we're going to look at both shapes. So this is my page 2. So we're going to look at f of x equals 2 to the x. That's a perfect example. And we're going to look at f of x equals 1/2 to the x power. Exactly what you came up with. Okay, so if you remember, I mentioned several functions that are friendly. The exponential function is friendly, meaning the domain is all real numbers. So we're going to talk about the characteristics and graphs for both. Okay, so domain, all real numbers. We can raise 2 to any number, positive or negative. The base is restricted, but x is not. Okay. Now, how do I graph something like this? An exponential function with a base greater than 1. So the graph will always be increasing on all its domain. It will look like this. So this is the graph of 2 to the x. As you see, it's increasing. So I'm going to write all these properties. Oops, I lost my page. I lost my page 1. So f increasing on all its domain. It has another property. It has a horizontal asymptote. Horizontal asymptote y equals 0. Meaning it gets closer and closer, closer and closer to 0, never touching it. Or we say eventually, maybe. Can anyone give us the limit as x approaches negative infinity from 2 to the x, as well as the limit as x approaches infinity from 2 to the x? Look at the graph and tell me what I should write. The limit as x approaches negative infinity, and the limit as x approaches infinity. Anyone, please? From the graph, can anyone identify the limit of 2 to the x as x approaches negative infinity?
Negative infinity.
Let's take a look. As x approaches negative infinity, the function values get closer and closer, closer and closer, closer and closer to what value?
0.
Yes. Excellent. Good. Now, the other end, as x approaches positive infinity, the function values get closer and closer, closer and closer, closer and closer to
Positive infinity.
excellent. Perfect. Okay. As you see, there is no x-intercept. No x-intercept. But what about the y-intercept? Can anyone give us the y-intercept of this function? How do we determine the y-intercept when x is?
Zero.
Yes. So please plug in 0 and tell me what is this point. Very important to remember.
2.
2 raised to 0.
0.
Careful. Let's talk about this. any number raised to 0 is 1, making sure that a is not 0. How come? If you remember, we had two indeterminate cases. This is one of them, 0 raised to 0. So that's why any number raised to 0 is 1, but 0 raised to 0 is an indeterminate case. We don't know what the outcome is. Okay? So please remember, any number raised to 0 equals 1. So coming back, then the y-intercept is?
1,
Yes, but in an ordered pair format.
0, 1.
Perfect. Good. Okay, finally, I just want to determine the range, and then I'll move to the other shape. Can anyone give us the range of this function? And I'm going to put it right here. The range of this function. Very easy, by looking at the graph, we know. Can anyone give us the range of this function?
Would it be 0 to positive infinity?
Absolutely, thank you very much. Perfect. Good, let's move on to the other shape. It's an identical situation, but a decreasing graph, a decreasing function. So this is 1/2 raised to the x power. So this will be the case for any function, exponential function, with a base greater than 1. And we have two special ones that I'm going to talk about in a minute. So let's talk about this one. The range, there is no difference. The range is the same, 0 to infinity. The only thing that happens, or I should say here, that changes. So no x-intercept, 0, 1 is the y-intercept. The limits will be different. The horizontal asymptote is the same. And the fact that this function is decreasing on negative infinity, infinity. So now let's only determine the limits because there is no other change. So can anyone tell us the limit of 1/2 to the x as x approaches negative infinity, and limit of 1/2 to the x as x approaches positive infinity? Everything else is the same. Same domain, same range, same same y-intercept, same horizontal asymptote. What about the limits? Can anyone give us the limits? Anyone, please?
For the x as it reaches to negative infinity, is it just positive infinity?
Of course. Whoops. That's where it's going. Good. And what about the other one? The other end?
0.
Yeah, absolutely 0. Very easy to see. As x approaches infinity, the function values get closer and closer, closer and closer, closer and closer to 0. Excellent. We do have two special exponential functions. Both of them have bases greater than 1. So we have f of x equals e to the x. And we have f of x equals 10 to the x. Why are they so special? So I'm just going to share my screen right now. Here they are. As you see right here, 10 to the x in blue, which is activated with the second key, right here, 10 to the x, and the other one is e to the x. Both of them have bases e to the x. So if you, in case you want to see what e is, all you have to do is press the second key and the division symbol and press enter, and you will get 8, 9 digits of e. It's called Euler's number. Euler's number. He came up with, this mathematician came up with e to the x, I should say with e, because he found that this base fits a lot of real life situations. E to the x models a lot of different real life phenomena. So this is your e. Now, if you want to graph, just quickly so you can see the graphs of 10 to the x. So I want 10 to the x. And I want e to the x. And you will see what happens. So the first one is purple, the other one is red. Let me use the standard because I don't know what I had in there. Here's the blue, here's the red. If a student copies these graphs as you see them here, I know that the student didn't pay attention in class. So here's why. Notice that they both, when x is 0, both are 1. So of course they cross the y-axis at the same point. They have the same y-intercept. But I don't want to see a graph like this. So if we want to graph these two, or any, please make sure that you don't graph something like this. Okay? So if a student copies this, then I know the student didn't pay attention in class. This is incorrect. So the correct graph is this. Okay? The exponential function is not 0 here. It only has a limit that is 0. The tendency, but not the value. So please do not graph something like this. Okay? This is how the graph looks like. At least from the distance, this is how it looks like. Blue and red are overlapping each other from -10 to -1, and then all of a sudden they take off. The higher the base, of course, the closer the number is to the y-axis. Okay, so these are very useful. They both have a basis greater than 1, and they have special names. This is called natural exponential function. This is called, yes, this is called common exponential function. So base 10 is common, and base e is natural. Okay, I retrieved my page 1. Good. Now, what I wanted to continue with is, if you remember, when we talked about compound interest a long time ago, 5 weeks ago, we wrote the formula a equals p 1 plus r over n raised to nt. But this is compound interest n times per year. That's the compound. But we also have continuously compound interest. I couldn't show it to you because this formula involves an exponential function with a base e to rt. P is the same, r is the same, t is in years. But we did not discuss at that time anything about base e, so I could not talk about the continuous compound interest. So I'd like to start with a problem on continuous compound interest. We do not have to. Where's my book here? Where's my book? Here's my book. And this is on page 203. We should focus only on the because it says find the future value of the investment when interest is compounded annually. We know monthly, daily. We did all that. So let's just choose the continuous part on any problem you would like to work on. Anything from 9 to 16. Okay.
Can we do 11?
Yes. So let's look at 11. So the annual interest rate is given to us, and the time is given. However, the time in the formula is in years. Find the future value of the investment when such and such. Then D is continuously, and let's also look at part E. Then find E, the doubling time, it's called T, for the given interest rate. So we're going to discuss both situations. Okay, so we said number 11, so let's continue with number 11. This is my page 4. Let me see, the video is okay. No,